we're continuing on with what we were looking at last week, which was how to build classes, how to look at copy control, and particularly today we've got to look at a thing called move semantics. And before we get started, I had a question come in from a student last week, and they said this. They said, in the examples, for constructors and the getters and setters, we define inside the class declaration. However, all semester I've told you to separate the declarations and definitions, basically what gives. And you can see my example from last week up here for constructors, and these constructors being in this .h file. And inside this .h file, you can see the definition of how things work. And quite rightly pointed out that I was almost being a hypocrite because I told you not to do this, and I was doing exactly the thing I told you not to do. So I went away and did some looking, and basically what comes down to style, is style. And so if we think about this, the .h file or .hpp file is the public interface, okay? So everyone with your .h file can see all the function declarations and all the data members in your class, both public and private, okay? So your .h file is your public interface, but it also reveals actually what goes on inside your class in terms of what does the class store. And so what your class stores is not a secret, okay? But how the class uses that data might be a secret, okay? So this goes all the way back to week 1 when we were talking about this third-party class library. You might get a header file, and you might get an object file, okay? So specific implementations of methods should be inside the .cpp file, okay? Because you might want to protect that information. However, simple constructors, getters, and setters that are not complex or don't do anything amazing or secret with your data, they're perfectly fine being inside the class declaration. It's a matter of style, so it's up to you. I do this. One of the tutors doesn't do this. He always separates the stuff out, okay? This is a matter of style, okay? So it's up to you what you do, okay? I'm not going to take marks off for if you do one of these approaches or a different approach. What I would take marks off for is if you did all your definitions of your functions inside the class declaration. So inline constructors, inline getters and setters are fine. It's a matter of style, okay? More complex things. So say there was a more complex method in the sales data example, you would not put that inside the .h file, okay? So it's a matter of style, and there's a Google style guide you can take a look at to do with inline functions. Okay, so recapping where we were on Thursday. On Thursday, we looked at copy control. And we talked about the big 5. So the big 5 in copy control is your copy constructor, your copy assignment operator, your move constructor, your move assignment operator, and your destructor. And we looked particularly at the copy constructor and the copy assignment operator and the differences between construction, initialization, and assignment. And so we're going to pick up where we left off in terms of that, but we're going to go a little bit further. This week, or at least today, we're going to be writing a stack-like class, okay? So last week, we did this sales data class. This week, we're looking at a stack-based class. And this stack-based class is designed to store data on a stack, okay? Now, there's 2 approaches you can take to when you're building containers like this. There's what's called a value-like class and a pointer-like class. And also the example I gave you last week was talking about if you've got an object, so I've got my cell phone here, you've got an object. If you put it inside a container, so I've got a bag, I'll put this inside. In terms of C++, when you put an object inside a container, the general principle is actually you copy that object inside, okay? And that's a value-like class. So the data I put in gets copied in. It doesn't get moved or referenced in, okay? And so class data members inside this container have their own state, okay? And so when I put an object inside something and I get a copy of it, these things are independent of each other, okay? So this is a value-like class. A pointer-like class is when what I put inside here gets referenced or gets pointed to. Okay, so then I only have one object, but I'm dealing with pointers. Okay, that's not to say I won't be dealing with pointers inside my value-like class. Okay, but it's to do with do I have one or multiple copies of objects, and are they independent or are they not independent of each other? And so, say if we have an object, we put it inside a container, and then we duplicate that container. In that duplicated container for a value-like class, I'm going to have a complete duplicate of all that data. In a pointer-like class, I'm going to have a duplicate of all the pointers, but what those things are referencing, I'm only going to have one object of that. Okay? So keep that in the back of your mind. You've got these pointer-like classes, so you've got these value-like classes, and you've got these pointer-like classes. We're going to spend the next hour looking at a value-like class. And so what we're going to do is we're going to build a stack, okay? And there's a whole lot of code here, okay? I don't expect you to read all this code, okay? But the key thing is we've got this stack, okay? It's called ubstack.h, and it contains a whole lot of public methods, okay? And it contains some private data. One of the things it contains is a private forward declaration of a nested class. So we have a class inside another class, and that internal class is private. So this value-like class that we're building, this value-like container for a stack, has a private class inside it called node. And this node is where we actually store the data that's stored inside the stack. It's also got this private method called reverse, and it's got a private pointer to the first node in our stack. Okay? That's the key take-home from that header file there. We've got a number of function declarations, okay? But the particular thing of what this class is storing is it's only storing one thing. It's storing a pointer to a node. It's the only thing that the stack is storing, pointer to a node. And this is a value-like class. So if we go and look at how this thing is implemented, okay? We have this nested class. This is inside our CPP file, by the way. This is now a nested class. We have a class called node. The nested class is a friend of the outer class. What this means is the outer class can access all the information within that inner class, within that node. Okay? And this is completely self-contained here. So I have a constructor for the node and a destructor for the node. And the node itself contains an item. So in this particular case, because this isn't strictly a generic type, our stack is only storing ints. Each node in our stack is an int. That's a value. Each node in our stack also contains a pointer to the next node. Okay? Hopefully you've recognized the structure maybe from first year. This is basically a singly linked list. Okay? This is basically a singly linked list that we're making behave like a stack. Okay? So we've got this nested inner class. Okay? Don't need to worry exactly about how this code is working, you just need the idea, okay? We then have a whole lot of methods on the stack itself. So we've got a constructor, which constructs the stack, and there's no data initially in there. So the head points to null. We've got a copy constructor. We'll go into that in a few minutes. We have a destructor. We have some methods to return top, okay? And what you should note here is we've got two methods for top. We've got a const version and a non-const version, okay, for const correctness. We have some methods called empty, and we've got some methods called fill. If you look carefully at this slide, sorry, they're missing the bracing. There is bracing there, it's just for LaTeX compilers lost the bracing. So it should be bracing on there. There's a method called reverse, which reverses a stack and pushes some stuff. So this is how we actually copy it. Okay, again, don't worry too much about how this works. It's just we've got a method. We've got a push, which pushes a new item onto the stack. Okay, this one's important. This is how we do the value-like semantics. We take a reference to the thing that we're going to push on to the stack, and then we make a copy of it by creating a new node, and we copy it over. Okay, so this is why it's a value-like class. We have a copy assignment operator. Okay, so you guys who are here on Thursday, we looked at copy assignment operators. We've got a method called pop, as you can imagine, takes the top off the stack. We've got a top here. Okay, we've actually got a second top. So again, there's a duplicate on these slides. There's two top methods. That isn't quite right. We've got a move constructor, which we'll talk about in a few minutes. We have a move assignment operator, which we'll talk about as well. And finally, we have a swap function. And a swap function swaps two stacks. Again, don't worry about how this code works. We're going to talk about it. And so those 9 slides there, all the code that we're going to be talking about for the rest of today. Okay. Oh, and one more. So this is how the client might go and use the stack. It might say, create me a stack, push some data on it, pop some data out, print off the top. Okay. So on the right-hand side here, I also have the implementation of all this, and it compiles, or at least it did compile until I probably broke it. But it does compile. It's the version that you can download should. And so now we're going to break down and take a look at how this stuff works. So we're going to start with the destructor. The destructor, what does the destructor do? So on Thursday we might have talked about destructor. What does a destructor do and how is it different from a constructor? Can somebody tell me? Yeah, it deletes everything, but how does it delete everything? Sorry? Recursively? No, not quite. How does the destructor work, and how is it different or opposite to the constructor?
According to when something reaches the end of its scope,
Yeah.
the destructor is called to make sure it is deleted safely.
Yep, the destructor is called when something goes out of scope, yep. But in particular, we talked about, okay, let's go back and talk about construction. How do we construct objects? What should we do when we construct objects? Like, we should initialize them, right? What order should we initialize things in? For order of declaration. For the destructor, what order should we destruct things in? The reverse order of declaration. Okay? We have to make sure we get that right. So the destructor is reverse order of declaration. I'll say it now. There's actually a question in your exam on that. Okay? So you should notice constructors compile stuff in, or construct stuff in the order of declaration. Destructors, reverse order. Okay? And so if we don't provide a destructor, we get one created automatically for us. Okay? The compiler-generated destructor looks like the very top line up there. It does nothing. There's nothing in this bracing. Okay, so the compiler-generated destructor doesn't do anything. What it will do is it will call the reverse declaration order destructors on your data members, but it doesn't do anything inside this bracing. Okay? Now, the class that we just very quickly put together, if we go back and take a look at it, it contained a pointer to something. And when we added something on, we created that object. Okay? And so that pointer got set to equal to the first node. Okay? And so if we have some code on the left-hand side that says, create me a stack, push 4 numbers onto it, and go out of scope, the destructor that doesn't do anything will delete the pointer to the head after it gets destructed. Okay, as in that pointer object will be disappeared, but the data that's being referenced or pointed to on the heap that was created through all the calls to new to copy all that data over is still there. And now we have a memory leak. Okay? So the compiler-generated destructor causes this big memory leak because we have dynamic memory. Okay? Our destructor, which is only 1 line long, says delete head. Remember, head is a pointer. So what that does So this destructor goes and deletes the head. Now, as a pointer to a node, and our inner class on node also had a constructor, which said delete next. And so it goes off and deletes next. And next is also a node. And so it goes off and deletes next. And you start to get the idea, it starts to clean up all this memory automatically for us. So it recursively goes down. Well, it's not even recursive, but it goes through all the nodes and deletes them. Okay? So our destructor works. Okay, we've actually got two destructors in this code. We've got a stack destructor and we've got a node destructor. The stack destructor, if I can find it again, there it is. A stack destructor calls the very top of our linked list and says delete on that. The very top node on the linked list says delete the next thing in the linked list, and so on and so forth. Okay? So this works. So the compiler-generated destructor, because we're using dynamic memory, doesn't work. Leaks memory. R1 does. Let's take a look at the copy constructor. Can someone tell me what the difference between a shallow copy and a deep copy is? Yeah, just yell out.
Shallow copy just copies the stack class.
Yep.
Deep copy will go through and copy all the memory, the values that are stored in it as well.
Yeah, so that's exactly right. So the shallow copy will just copy that stack class. The deep copy will copy all the inner data, the values, the nodes, and will copy that as well. So a deep copy is a complete independent copy. And that's what we wanted because we're doing a value-like class. But by default, the compiler-generated copy constructor does a shallow copy. It only copies the stack class, not the node class. Okay? So in this case, we've got an example here. Before we did for copy, we had a stack which has got a head pointing to a node, and the node's got then 4, 3, 2, 1, all pointed into it. When we did the shallow copy, so we say UB stack S2, copy in S1, okay? This is a universal initialization, which you would have seen on Thursday. You end up with two stacks both referencing the same data. And so you don't have value-like semantics. And this can also lead to memory corruption errors. Can anyone think about how this could lead to a memory corruption error?
You deconstruct one, but not the other, and then you try to use the other to access the nodes.
Correct. So if we delete one of these stacks, and we correctly call the destructor, which we just defined, we've now deleted all the memory, and we've got a second one that thinks all that memory is still there, and this is how you get memory corruption. Okay? So as a general rule is if you define one of the big five, so either the destructor or the copy constructor, copy assignment, move constructor, move assignment, if you define one of those, you've got to define all five of them. Okay? If you define one, you need to define all five. Okay? So how do we fix this? Our one's very simple. Our copy constructor, again, is one line because it calls another method. Okay? Our copy constructor, which is up here on line 35, calls this method called reverse. And reverse is defined actually just above that. And it says, again, it's the recursive method. It just goes down. It goes down a set of nodes to the last one, and then it pushes whatever that last one is pointing to. It pushes that onto this new object that's being constructed, okay? And it keeps going like that. And so this reverse function basically duplicates the stack correctly. Again, you don't have to worry too much about how this code works, and if you find a problem with it, let me know, okay? But you need to get the idea of how these things are working. So the compiler default copy constructor just copied our stack. Our copy constructor went down the entire stack, the entire set of data that was being stored, and copied each one of those, put it into a complete duplicated object. Okay? And again, down the bottom, we can see what we had before, which was stack 1 pointing to this data, And then afterwards, we've got stack 1, stack 2, and a complete duplicate of this data. So 4321 has been completely duplicated. All our nodes have been duplicated. Okay? Let's talk about copy assignment. This one gets to bring together both the deleting things and assigning things. First of all, can people tell me what the difference between initializing something and assigning something is? We talked about this on Thursday, so this is a recap from Thursday. What is the difference between assigning and initializing? If I ask you what the difference between a copy constructor is and a copy assignment operator is, because it's essentially the same question, what's the difference? What's the difference in how they operate? Yeah, just yell it out.
In the constructor, or the copy constructor,
Yep.
nothing's made yet, so you need to initialize everything.
Yep.
In the assignment, you have to change all of the values, which will
Yep.
copy all of the values over to already existing numbers.
Yeah, that last part's the important part. The copy constructor constructs a whole new object, and you initialize all these values. The copy assignment operator doesn't construct anything new. There's already something new. It replaces all the values that are already contained inside an object. Okay? So, again, the compiler automatically generates one of these things for us. Okay? And the version that it generates for us copies correctly, but incorrectly, but copies the stack class over. Okay? And so before, we might have 2 stacks. And now we want to assign stack 1 to stack 2. So we want to replace what's inside stack 2 with everything inside stack 1. The compiler-generated copy assignment operator moves the head pointer and leaves all this other data pointing to nowhere. And so again, we've leaked memory. And again, it's not working as we expect, okay? So you need to pay close attention to the slide down the bottom. We have 2 stacks. The default compiler-generated copy assignment operator has just moved the pointer to the first thing. And now we've got this memory being leaked. Okay? On the next slide, I'm going to show you how we solve this. We solve this by doing this approach. We start out with 2 complete stacks. What we want is still 2 complete stacks, but it's copy assignment. And so we need to copy everything that was in stack 1 across into stack 2, and we need to free all the data that was previously in stack 2. So you see this 5555, we need to get rid of that data. We want to replace that data. We want to replace it with a copy of 4321. Okay? So I'm going to jump back to the previous slide. Previous slide didn't do that at all. It didn't get rid of 5555. What's worse is it just sent the pointer to the same location of memory of 4321. It didn't do any sort of copy of what we wanted it to do. Okay? And so on the next slide, this is what we actually want to have happened. How do we do it? First step, check that what you're assigning to isn't yourself. Okay? If you assign to yourself, which is perfectly valid, you can say S1 equals S1. Perfectly valid, and that copy assignment operator function is going to be called. You do not want to delete the memory that you're pointing to yourself. Okay? So step 1, check that you're not pointing to yourself. Step 2, delete the stuff that you're currently in your stack, that's currently contained in your stack, because you want to replace that data. Okay, so delete the data you're currently storing. Then, set your head off to nowhere, because you've deleted everything. Okay, so we've got to fix up that pointer. We say it's equal to null pointer, so we don't get a memory corruption error. We then, very similar to our copy constructor, we call this reverse function, and its reverse function nicely now copies the data across. And finally, we then return a reference or pointer, return the dereference of this pointer from that function. Can we see how that worked? Okay. You'll have to probably go across some of the stuff by yourself later on to get the feel for it. And every class that you write will be different, depending on how it's operating. Okay? This stuff's important to assignment 3. You haven't got assignment 3 yet, but this is important to assignment 3. It's also important to assignment 2, but assignment 2 you don't have dynamic memory. So assignment 2 you'll have to do some stuff with copy constructors, not quite as much of this dynamic memory stuff. But assignment 3 you'll have to do the stuff with dynamic memory. Okay, so it becomes quite complex. Now, copy semantics has limitations. Okay? We have a function here we've called makeStack. And this makeStack function creates a UB-stack object, okay, so a constructor gets called. We then go into a loop and just read from standard in. And so we just keep on reading some numbers, and every time we read a number, we push it into the stack. Okay? And then this makeStack returns the stack that was made at that point. Now, there's no problem with this code, okay? There's no problem in terms of the syntax of this code, but in terms of performance, this code isn't the best. The reason why this code isn't the best is this local variable, this UB stack here, has to be copied when it gets returned. So when we say UB stack S1 equals makeStack goes off and makes a local stack there, and then returns, it has to call the copy constructor. Now, we can't return by reference because we should not be referencing a local variable. Okay? But we kind of seem like we're wasting some performance here because we just gone and created something, and we didn't really intend to copy it, but now we're having to call a copy constructor, okay? Because at this point, this line 9, this copy assignment operator is being called. Copy constructor is being called, not copy assignment. This is for copy constructors being called at this point, okay? Now, the point at the bottom of the slide is the compiler may optimize some of these calls to copy constructors away. Okay, so in this case in particular, the compiler will probably save you and do some fancy stuff to not have to worry about this. But there's plenty of other examples where we don't intend to actually copy something, we want to actually move something. And so C++11 introduces a thing called move semantics. And so move semantics are used where you want to move some data rather than copy some data. Often you want to move some data because the thing that's currently referring to that data is about to go out of scope or be destroyed or something else is going to happen to it. And so probably a good example of this is swapping. Here's a function called stack swap. This is using standard copy constructors. In order to swap these two stacks, we call the copy constructor on S1, so on temp, and copy in S1. We then call the copy assignment operator to make S1 equal to S2. We then call the copy assignment operator to make S2 is equal to temp. And so there's a whole lot of copies that have gone on here. This is a very slow process, a swap. Okay? And so the question is, can we do this more efficiently? And so move semantics allow us to do it. They give us, we've been talking about L value references so far, we're about to start talking about R value references. Okay? And it will give you a huge performance improvement in your code. Okay? So the question that we ask when we're moving some data around or copying some data around is the data that we're going to be copying from persistent and will be used again? Okay, so do we want a complete copy? Or is it a temporary thing that's going to be destroyed? In that case, we want to move it. Okay? And again, this slide basically summarizes what I've been saying on the previous slide. Okay? So we want to do something whereabouts we want to copy some or move some data from a source to a destination. Okay? We do this by creating a move constructor and a move assignment operator. The difference in the function prototype signatures is simply a double ampersand as opposed to a single ampersand. Okay, so this is where about comments might help you out a lot, because just glancing at the code and going, why is that a single ampersand, why is that a double ampersand, that's going to get really confusing really quickly. But the single ampersand is an L value reference. Okay, it refers to memory location or something. The double ampersand is an R value reference. It refers to the value at a particular location. Okay, so the copy and the move constructors are overloaded constructors. The copy and move assignment operators are overloaded functions. The implementation of these things looks a bit like this. The move constructor calls this thing called standard move and moves this head pointer across. The thing it's moving from is now assigned to a null pointer. Okay, the reason why it gets assigned to the null pointer is because that thing's about to get deleted. And for similar reasons to all the things above that we saw with when we get these moves and these copies wrong, we don't want to end up deleting memory that we shouldn't delete. Okay? So the move constructor moves the head pointer and then sets that current head pointer off to be null, because the destructor is going to get called in that data. The move assignment operator looks very, very, very similar to our copy constructor. Move assignment operator looks very, very similar to our copy assignment operator. First of all, it deletes all the data that we're going to be copying over the top of, okay, because we need to clean that up. We then move that head pointer, and then unlike what we're doing previously when we're calling reverse, we don't need to call this reverse function anymore, okay, because we don't want to do a complete copy. We just need to move that head pointer, and then the thing we're about to destroy, we set its head pointer off to null, and it works. We can think about this that we are stealing resources from another object. We have an object, we're just going in and taking all the data we want. We're just gutting it, okay? We're taking that resources, we're stealing that resource from another object and putting it into either a new object or overriding some values, depending on if you're doing assignment or initialization, okay? Now, a really important point to make at this point is after you've moved some data from an object, so after we've called the move constructor or move assignment operator, at this point, the destructor from that thing that we moved from is not called. It's not called until we go out of scope. Okay? That means that the object that we had before, we moved from, still exists in memory, and its state is undefined, and definitely don't use it. But its state is formally undefined. Okay? You got a question, or are you thinking about one?
Yeah.
Yep.
Well, what I want to know is, when does this get used?
When does this get used? We're going to get to there.
Okay.
Okay? We've got some examples coming up, okay? But think about the swap. All this is leading to is how do we do a swap efficiently, okay? So we're stealing these resources, okay? We're gutting out an object, okay? So it's really important to state once we've moved from an object, the object we moved from, its state is undefined. It still exists until it goes out of scope. And again, we need to make sure we do this correctly, because otherwise when the destructor gets called for this object that we're moving from, if we haven't done it correctly, the thing that we've moved to could be potentially have bits and pieces of it destroyed by accident. Okay? So, for a compiler synthesized move constructor move assignment operator, it's provided if none of the big three is provided. The big three is pre-C++11. Big three is your copy constructor, your copy assignment, and your destructor. It became big five with C++11, which is this move semantic stuff. Okay? And so the way in which the constructor or the assignment works is it calls the member functions, move constructor, move assignment of each member, data member inside a class. Okay? Built-in types like ints, floats, doubles, they're just copied. They're not moved, they're copied. Array members, like C-style array members, are copied. Okay? So even though there's a move constructor, some copies still go on depending on the data types. Okay? for our UB stack class, the compiler-generated versions of them are wrong. Okay? The compiler-generated version of the move constructor just says move for head. And that's what you think it might want to do. You just move for head. This is wrong because what's going to happen is when we call delete, it's going to end up deleting the stuff that we moved from. The move assignment operator does exactly the same thing. Okay? Now, I'm going to come to this in a few slides' time, but also note the word no except on the end of these constructors. Okay, you don't need to write no except. For compiler, we'll put it in automatically for you, but this means something, which I'll explain in a few slides' time. So let's look at the compiler-generated move constructor. Like I said, it's wrong. The reason why it's wrong is because of this. You might use it in this case. UB stack S2 equals standard move S1. And so before we had S1, it pointed to this data. Afterwards, we have S1 and S2 both pointing to this data. And now when S1 dies, so it goes out of scope, the destructor for S1 is called, and this commonly shared stack memory gets freed. And now S2 points to something that's been freed in memory, and we have a memory corruption. How do we fix it? Actually quite simple. We move the head pointer. Okay, so it's not copying all the little bits and pieces of data we copied before. Okay, because we're moving, let's move that head pointer. But where we copied from, we set it to null. And so we have before S1 pointing to this data. After S2 points to this data, S1 points off to the null pointer. When S1 gets destroyed, it doesn't go and wipe out all our memory that we moved from. Okay? Same applies to the move assignment operator. The compiler-generated version of it is wrong. Imagine we had two stacks like this, 4321 and 5555. And we want to move S1 onto S2. If we do that, we have S1 and S2 both pointing to 4321. 55555 leaks, and then when S1 goes out of scope, 4321 gets destroyed. We've got multiple problems going on at this point. Okay? So how do we fix it? Very similar to before. Okay? We delete the 5555 stuff. We move the pointer for S2 to where S1 is pointing to. We set the S1 pointer off to null. And it works. And does what we expect it to do. Now again, how each of these things work will depend on the particular problem that you're trying to solve. So this solution here is for our UB stack class. It isn't the general solution for every program that you're going to write. Every program that you're going to write will probably have a different way of doing this stuff, but you need to think about how the stuff's operating, what's happening with the memory underneath. Okay? So we've moved the data, and it's worked. Now, a final thing I do want to mention at this point is no except. No except is a tag that we can put after our function definitions. So, say this copy assignment operator I've got sitting here on this right-hand side, I can write the word no except into here like that. The purpose of that, and we're going to talk about exceptions next week, okay? But the purpose of that is to say to the compiler that there's not going to be any exceptions thrown out of this method. Okay? This is really, really important for a copy constructor, for a destructor, and for a copy assignment operator. Now, does everyone know what exceptions are? Like try and cache. Does everyone know what exceptions are? Okay? We're going to talk about C++ versions of them next week, but you need the general idea. Try and accept is try to do something. If it doesn't work, throw an error message, or maybe not an error message, but throw something and catch it and internally handle that problem. The reason why you cannot throw out of a constructor or a destructor or move assignment operator is if we throw out of the middle of those things, we don't know if we've half constructed an object, we don't know if we've half destructed an object, we have no idea. So no except is provided automatically for those big 5, but you can also put it onto your own code where you don't have things throwing exceptions, particularly where things shouldn't throw exceptions. And 2 things will happen. It's not going to have an error at compile time. It might give you a warning. I actually don't know. I haven't tried. If you maybe you want to do this in your own time later on, try to see if you can throw an exception and see if it will compile on something that's tagged no except. But more importantly, at runtime, if you throw an exception out of a no except function, or, and we're going to talk about this next week, or if some functions that you've called up the stack throw an exception and you don't catch them, and they end up in a no except, e.g. a destructor, what happens to your program at runtime is your program just crashes and terminates. And it says, I'm not allowed to throw out of a no except function. Okay, so we're going to revisit this next week. This is really important to know that your constructor, your destructor, your move and copy assignment operators should not throw exceptions. If an error occurs at that point, you need to be able to handle it within those functions. Okay? And there's a reference there that you can read more about the stuff as well. Okay, so let's come back and talk about L value and L values. We talked about references back in week 1, and we showed you references. We also talked about L values and L values and R values in week 1. And an L value is an object's identity or its address in memory. An R value is for object's value at that point in memory. Okay? And so we can do things like this. With an L value, we can say int I is equal to 1. I is an L value. 1 is an R value. Okay, so we can assign to L values. We can have something like this. Return by reference. So int reference get ref returns I. That returns an L value reference. Okay? And so get ref is an L value. Plus equals 1 works because it returns this L value reference to this I. Okay, and say its I is up here, so it's a pretty dumb function anyway. I is equal to 2. Guess what gets assigned at that point. Now, that's a very dumb piece of code. Don't ever write code like that, okay? But that will work. With R values, like this, okay, so this returns an int. It doesn't return a reference, it returns an int. So it returns a value or an R value. Int I is equal to 0. I being an L value, R being an R value. I plus 1 is an R value. So an L value plus an R value on that side. Okay, so that I there's an L value. For R is an R value. I plus 1 is actually an R value. It's a value. Okay, you can assign that into I, and then you can return I. It's return I because it's returning a copy is returning an R value. And so we can't say get val plus equals 1. Doesn't make any sense. We can say get ref plus equals 1. That makes sense. But get val plus equals 1 doesn't. And it's because of return types here. This is an L value, which is on the left-hand side normally, okay, but it returns to a memory address. Okay? And so if get ref plus equals 1 is basically saying at the memory address of get equals, at memory address of get ref plus whatever's stored in there by 1. What this version is saying, get val, is saying the value of whatever that thing's returning, so in this case 1, plus equals 1, store that wherever 1's being stored. That just doesn't make any sense. It doesn't compute. Okay? So L values, left-hand side, address in memory. R values are value. This gets really important for move semantics. An L value reference is formed by placing an ampersand after a type. Okay, so this is what we would have seen in week 1. We have a class A. We can have a reference, or an L value reference to class A, which is essentially an alias. An L value reference isn't strictly a type in its own sense. It's an alias for whatever is being stored up here. An R-value reference is formed by placing 2 ampersands after a type. So we can create an R-value reference like this. Okay, it's not recommended to do this, but you can do this. Okay? And so we can then create an R-value reference by going A plus A. This A plus A itself is an R-value. Okay? And so an R-value reference behaves just like an L-value reference, except that it binds to a temporary object. Okay, so temporary objects are R-values. And you cannot bind a non-const L-value reference to an R-value. What that means, number 1 down here, line 1, create me a reference to A. We can't create a reference to a temporary object like this. The reason why we can't do that is because this A that we're constructing at this point becomes an R value because it's on the right-hand side. We can't do this. We could do it up on the top line here because this was L value. You can't do it down here. We can do it with the R value reference. Please don't do this. This is quite dumb. Okay, but you can do A ampersand ampersand, so make an R value reference to this temporary object on the right-hand side. Don't do that, but you can. What's the point? We're going to get to a point, okay? You need to understand how this is all going, okay? We're getting to a point. So, in general, L-value references are persistent, and every named variable has an L-value reference, or is an L-value reference. Okay, so everything is a named type. Every variable is an L-value. R-values are bound to objects that are about to be destroyed, or are temporary, or don't have any user or ownership anymore. Okay? So R-values generally reference temporary objects. Okay? Now, some of you guys who might know a little bit more about C++ than even I do, if I get this wrong, you can happily tell me. Okay? Or if you've got a better example of explaining this, you can also happily tell me, because this is complex. So, let's look at how L-value references and R-value references work. L-value references are, well, functions that return an L-value. Plus plus I is an L-value. Okay, pre-increment is an L-value. Dereference, so star P, is an R-value, is an L-value. Get me the location 2 in an array is an L-value. Okay, these things are all named types, named variables. R-values are functions that return non-reference types. So functions that return by value are R-values. I plus plus, post-increment, is an R-value. Okay, it's afterwards. I plus j is an R-value. It's a temporary object that I plus j gets to be a temporary object. I less than k, the Boolean returned by that, is a temporary object. Okay, so all these things are temporary objects and are R-value references. Okay. So let's come back and look at the swap. This is where it all hopefully makes sense. Previously, stack swap, okay, involved a copy constructor, a copy assignment, and a copy assignment. And so there's a whole lot of copies going on in memory at that point. A whole lot of new nodes being created, old nodes being destroyed, and it was slow. With move semantics, we can do this. We can move stack S1 into temp. Okay, so we still need 3 variables. We move stack 1 into temp. We move stack 2 across to stack 1. And then we move temp across to stack 2. And so, in this case, standard move converts its argument into an R value. So a standard move function, it gets an L value and returns an R value. Okay? And so that's how the move-related copy control members can work. Note, standard move is potentially a destructive read. The reason why it's a destructive read is if you move something, you do not know the state of a thing that you move from afterwards. So we call it a destructive read. It reads the stuff and potentially destructs or destroys or moves or does something to the state of these things. Okay? So be very careful with standard move. Now, we don't actually need to write stack swap ourselves. There's one already in the C++ library. Okay, it's a templated function doing exactly what you just saw there. This is how standard swap works in the C++ library. It does it by move constructors, which is kind of why you guys need to make sure your move constructors do the right thing. So I'm going to take a break in about 5 minutes' time, but I'm going to shove 5 more slides into your minds just to confuse you further. We're going to talk about a thing called argument-dependent lookup. And so we've been talking about scope quite a bit over the last few weeks, and namespaces and why you shouldn't use namespace standard and things like that. Okay? So let's go and revisit some of that stuff. We have a namespace A. Namespace A contains a struct X. Struct X actually doesn't contain anything aside it. Namespace A also contains a function void if, which takes in a reference, an L value reference to X, and doesn't do anything. Okay? And so we can say this, we can create an X by saying A : capital X, lowercase x. So we create an L value at this point. We create a variable X of type struct X from namespace A. Now, without having to call A : f, we can just say fx. And the compiler works out what we mean at this point. Okay? And so what happens is the normal name lookup for if is performed and finds that there's no if in the in the global scope at this point. And so secondly, the lookup for if in the namespace scope where if is defined is found. Okay? So this is called argument-dependent lookup. Okay? It goes, looks up where these arguments are defined, and goes and figures it out from there. This is both really confusing and really powerful. Here is ubstack.h here. Okay? Our ubstack.h, let me get it right, okay, has a friend function called swap. Not standard swap, it's got its own function called swap. And swap takes in 2 L value references, so 2 normal references, to 2 stacks, and we're going to swap these stacks, okay? And this version of stack is going to be faster than standard swap. And everyone's going to be really confused at this point because we've just gone through how move semantics is so much faster than copy. We can go faster than move semantics. Okay, so we're going to write a version of standard swap that's faster than the move semantics. To do this, what our stack function does is it simply just swaps the pointers to the start of both of these stacks. Okay, so we don't have to swap all the data around. Even though we've got move constructors and move assignment operators to do it, we just got to swap for pointers. Okay? How this works is this stack function. Inside it has this thing that says using standard swap. Now I've told you don't use a namespace standard. I've told you don't do these things. Now I'm showing you where you can do it. See how it's inside this function? So it's using standard swap, it's only going to exist inside this function. And the reason for that is this swap, depending on what these pointers are, using this thing called ADL, so it's argument deduction lookup, what it does is it goes, okay, should I use this swap? Should I use some other custom swap that's defined somewhere else? Or should I go use standard swap? And it works it out based on the arguments that are passed into it. Okay? So to confuse you a whole lot more on namespaces, this is ADL. So what it's saying is, if there's a type-specific version of swap defined, go and use it. Otherwise, use standard swap. If I put standard swap just in front of line 9 here, everything would always use standard swap. So this code is basically saying, I'm deliberately polluting my namespace, I'm deliberately bringing a whole ton of swap things in, and leaving up to the compiler to figure out what the best way of doing it is. Okay? This is confusing. There will not be a question in the exam about this. Question.
How is this different from saying STD colon swap?
That's what I was just saying to you. If there is a different version of swap defined elsewhere that takes those particular pointers, it will get called. Okay, so this is why it's working out based on the arguments going in, which version to call. This is exactly what's going on. Go read the Wikipedia articles on this, or the references elsewhere. Okay? So, some advice, okay? Well, assignment 1, it's a little bit too late for talking about assignment 1, but use VSTL containers wherever possible. I'm going to come to your question in a minute, okay? Use VSTL containers wherever possible, and you don't have to worry about copy control. But sometimes you do need to write your own containers. So you have to write your own containers for assignment 2. You have to write your own containers for assignment 3. Okay? If you want your class to behave like a value, you need to manage your own copy control, which has been what we've gone through on Thursday last week and the first hour of this week. If you want your class to behave like a pointer, the best way of doing it is to use smart pointers with reference counting, which we're going to cover late next week, early the week after. Okay? Question?
Is it potentially slower to have the compiler decide which function to use in overloading?
Is it potentially slower for the compiler to decide what to use? It depends on what you're doing. It's the short version. It really depends on what you're doing. Sometimes you can be smarter than the compiler. So that's what we're seeing today. We can write this very fast version of swap. Okay? And we can outsmart the compiler on what it's doing. But there's other times that the compiler will do stuff a lot better than what you can, because people who have written it are going to know a whole lot more about what's going on underneath than you can even process at this point. And so that's one of the reasons why we tell you to go use VSTL containers rather than building your own. VSTL containers are used by everyone. Not only is your code going to be compatible with lots of other people's code, the reason why you go use VSTL containers is because what they're doing underneath is probably far faster and better than what you can possibly code, because they've had 20 or 30 years development underneath them. So it's a trade-off. Sometimes you might need to do your own thing. Sometimes you need to rely on what they're doing. Okay? So it's not a yes-no answer to that question. Okay, so at this point I'm going to stop for 5-10 minutes, and then we're going to talk about operator overloading. Okay? So that's the end of the first hour. Take 5 minutes. Okay, so let's resume. During the break, I had someone come and ask me a question, and they said, basically, why is this node class defined in the .cpp file? Okay, and also, why is this node class private? Why does somebody just want to go and modify the node class? The reason why it's in the .cpp file, the reason why the internal node class is entirely private, is because we don't want people messing with our internal data. Okay? So we can have a completely internal private class, in this case our node class, and we have it completely private because we don't want people messing with our internal data, which is the exact reason why you need to separate your declarations and your definitions and things like this. So in our public interface, in our UB stack class, we said we have this private node class. We said that we had a forward declaration of it, but we didn't give any more information about that class at that point inside our .h file that everyone's going to be able to see. Instead, in our .cpp file, we went and defined all the data for it and how it worked. Okay, so this is exactly getting to this point of the .h file is basically your public interface. If you want to hide off stuff, you can make these internal classes that are completely private, and you can handle stuff that way. And again, assignment 3, you'll be definitely doing this on assignment 3. Okay, so if you're confused about that, that's the internal class that's completely private, and we do not want to make that public, because if we make that public, something else can go and modify and mess with our internal data. We only want people modifying the data through the public interface that we've defined in our .h file. Okay? My advice to you, have a play. Move some stuff around, try to modify stuff, try to break things. It's the best way of learning. Okay. Second part of today, and for the rest of this week and possibly early next week, we are going to be looking at operator overloading, function objects, bind objects, and lambda functions. Okay? We're going to be looking at how we can build classes that can basically work with a whole ton of algorithms in the standard template library. And so operator overloading is a convenient shorthand. We're going to go back and talk a little bit about sales data class from last week. And our sales data class from last week had this method called print. And it got passed in a standard cout object, an O-stream object. And it got passed in as a result of this function called add d1, d2. And the question is, what's more intuitive to read, this print standard cout add d1, d2, or standard cout d1 plus d2? What one's more intuitive to read? I'm assuming everyone's going to say the second one is much easier to read. You can see it, that's got d1, d2, adding it together and printing it out. It's what you're used to seeing. And so C++ has a rich set of operators. Again, first week we showed you a huge table of operator precedents. Okay, there's a huge amount of them. We can define our own operators as well. And this is a really powerful feature of C++ that if you're coming from Java, you definitely don't see in Java. And so it's easy to remember that a plus should be a plus. Whereas it's hard to remember if we have a function called add, or a function called combine, or a function called sum. Plus is always going to be a plus. It allows you to reuse existing code. And allows you to provide a concise description of the task that you're trying to achieve. Okay? But there is one major disadvantage, which is the lack of context may disguise the meaning of what something is doing. Okay? So if we overload the plus operator to subtract, completely fine, you can do it, it's a dumb thing to do. But if we overload the plus operator to subtract, we can disguise the meaning and the context of what we're trying to do. Okay? So that's the introduction to operator overloading. So operator overloading is just a function. Okay? It's just a function within your class. The requirement is it must have one operand of your class inside it. Okay? What that means is your overload operator must do something on the class, or must it be involved with the class that you're operator overloading on. And there's some exceptions though. For order of evaluation, for or, and comma are not preserved when these operators are overloaded. You can overload double and, you can overload for or operator, you can overload for comma, okay? But it's really dumb. Don't do that. Okay? And you also can't invent new symbols, okay? So you can't change precedence, associarity, or arity of data, or how these things work, okay? But you can change how they operate, what they do when you call them. But do not overload for comma, for ampersand, for double ampersand, or for or symbol, okay? You'll be in a world of pain if you do that. Some operators, when you overload them, must be defined as class members. So assignment, so single equals, subscript operator, so square brackets, call, which are for rounded brackets, and member access arrows should be defined as class members. Some operators must be defined as friend functions, input-output operators, so input and output redirection must be defined as a friend function. Okay? And we're going to go through an example of each of these operators in the following slides. Sometimes we have a choice of what we do, whether we have them as class members or friend functions. Operators that change the state of a class or are closely linked to a class should be defined as members. Okay? E.g., compound assignment operators. So plus equals should be defined as a member function. Symmetric operators, such as just plus by itself, double equals, relational or bitwise operators are best defined as friend functions. The reason for that is, say if we've got a plus operator we're overloading. The plus operator returns a new object. When we say A plus B, we expect to then assign that to C. If I say A plus equals B, I expect that A to be modified. Okay? And do not overload operators in a way that change their normal behavior or meaning. Very important. Do not confuse people. So here's the first of our examples. The input-output operator. It must be defined as a friend function and is normally a non-member function. Okay? Normally a non-member function. The output operator takes arguments as a reference to an output stream and a const reference to the class type and returns the reference to the supplied output stream. What does it mean? It means in, say, your salesdata.h file, you have this output stream operator here. So this is a function called operator less than, returns a standard output stream reference, takes in a standard output stream reference, and a const sales data object. In your .cpp file, rather than doing like standard cout, this output stream reference, this OS variable you passed in, you just input redirect all your stuff out to that. And what that means now is when you say standard cout less than like sales data A, it calls this function and it prints out whatever this output stream is. Okay, so this allows us to override or to define what happens when we print out an object. Okay, fortunately I don't have any code to show you this happening. Okay, but you can go play with this yourself. Output redirection defines if we say we want to print out a class, what it actually prints out is. For input redirection is similar. Okay, you don't have to do this one for assignment 2. The input redirection takes some arguments, in particular input stream, a non-const reference to what it's being read into, and goes through and reads some data in. Okay? Don't worry about this one too much. This one is not in the assignment, okay? By the way, each of these slides with these examples, you can adapt off these slides for assignment 2. Okay? So output and input redirection need to be friend functions. Output redirection in particular needs to do something to do with how do I go and print this stuff? What does the print of printing out a sales data object look like? Okay? I don't have assignment 2 up on the screens, but in assignment 2 you're asked to print out a vector, the Euclidean vector, and you're asked to put some braces around it and then the data that's stored in each of those dimensions, magnitude in each of those dimensions. Adapt this code, giant hint, adapt this code. This is what you need. Talk about compound assignment operators. These are implemented as a member function. So our sales data thing last week, say if we wanted to combine 2 sales data objects. I do have this code. This code combine, where's it got to? We had this combine function. Okay, this function called combine. Let's do this with a plus equals instead. Right hand side here, this is our function from last week. Left hand side, let's do it as a function overload. Plus equals const sales data. Units sold plus equals. Revenue plus equals. Return star list. The return star list allows us to chain together multiple adds. So we can say A plus equals B plus equals C. Don't do that. Again, it's confusing, but you can do that all you like. Okay? And so you could do likewise with subtraction, with multiplication, with division. Again, adapt this code for assignment 2. But let's take a look at arithmetic operators. So let's go for plus. Okay? And again, last week we had this function called add. Okay, so right hand side we had this function called add last week. They took in const references to 2 sales data objects. Okay, produced a new sales data object. Okay, and then returned the new object. We can do that as a function overload. Operator plus takes in the 2 things we're going to add, creates a new object, makes that equal by copy construction to the first one, calls the plus equal operator we defined on the previous slide. Calls the plus equals operator we defined on the previous slide to add those two things together and then returns the sum. So this add operator created us a new object and then called the function that we defined previously to do the add and then returned it. Okay? This is quite a safe way of doing it. The reason why it's quite a safe way of doing it is because we have to define both the plus and the plus equals. If we're able to define the plus in terms of the plus equals, it means that we shouldn't get bugs in our code unless we have a bug in the plus equals code to start with, and then we've got the bug in both places. Okay? So can people see how this worked? How this plus operator called the plus equals operator we defined in the slide previous. Okay? Again, in assignment 2, you'll need to do a whole lot of this. Okay? You could probably nickname this lecture How to Do Assignment 2. Okay? Let's talk about relational operators. Relational operators are normally non-member functions. Okay? A relational operator is something that basically returns a built-in. Double equals, or not equals, or less than equal to. Okay? Classes with double equals and not equals often, but not always, have relational operators such as less than and less than equals. Okay? Less than equals, so less than, the less than operator is commonly used in associative STL containers and some STL algorithms. In particular, it's often used in standard sort. You should be able to, once you get to the end of this lecture, you should be able to write a less than operator for a class. Again, it depends on the class that you're defining. So I don't believe that we have a less than operator for a Euclidean vector assignment because it doesn't quite make sense. Okay? But for an int or a double or maybe even our sales data object, okay? Now, we don't have one defined for our sales data object, but maybe we had some way of saying one sales data object was less than another sales data object. Maybe the less than for that would be defined in terms of the number of units sold, or maybe it would be defined in terms of the price of objects, okay? This is up to you to define these things. The less than operator is really important because the STL algorithms use it, okay? There will be an exam question on the less than operator, okay? So throughout the semester you can take notes when I say there will be a question on something, okay? There will be a question on defining a less than operator in the exam, okay? Requirements for associative containers as well. If two objects are not equal to each other, then one should be less than the other. This is for associative containers in the STL, okay? However, for our sales data object, as I just pointed out, we are not going to define less than, and that's because there's no single logical definition for the less than operator with our sales data. Does less than mean the price of the sales data is less than the price of other sales data object, or does it mean the number of units sold is less? We don't know. Okay? So let's look at the equality operator. Equality is defined normally as a non-member function. I'm also going to pause here and ask you if you know what the difference between equality is and equals is. Do people think that they know what the difference between equality and equals is? Anyone can tell me? Yeah, go for it.
Is one like, are they the same object?
Yeah.
Is the other, they have the same value?
Yeah. So equals is often used to define when something is exactly equal. So in your case, in terms of talking about computer science, it might be, equals might be they are the same thing in memory. Okay? Not always, but this is commonly used. Equality is where they're equivalent. Equivalent might mean that they have the same value, but they're in two different places. Okay? So when we're talking about double equals here, we're actually talking about equality. We're talking about these things not strictly having the same location in memory, but being equivalent. What they store is equal in the sense of their values. Okay? So there's a subtle but important difference between equals and equality. Okay? Equality operators are normally defined as non-member functions. The reason why they're non-member functions is so we can use them in things like if statements. Okay? And so for our sales data object, okay, our double equals will check if the ISBN number is equal, the number of units sold is equal, and say if the revenue is equal. Okay, because this is complete equality. It's saying, are these things exactly the same? You might just define an equals as just being, oh, the ISBN number of these two books is the same. I don't care if the price is different. Again, it's up to you. That's why you've got this ability to overload functions. But you should make this clear. The way in which you make this clear is through good documentation and also through doing things that you expect to make sense. Also note on the bottom of that slide, line 11 through 13, the not equals operator. The not equals operator is defined as just reversing the double equals. Again, assignment 2, you have to do this. Your not equals is not double equals. Look at that, one line. Your not equals is one line. It just calls this double equals operator and just reverses it. Okay? So your not equals is literally for not equals, or not equivalent. Okay? So we are going to jump to a different example. By the way, there's a lot of examples for this week. Okay? So you'll have to download some of these if you want to have a play. But we have a small int class. And so we have small int.cpp, we have small int.h, and small int test.cpp. And small int, up on the left-hand side, we've got this class here that it's designed to have a sub-range of int. Maybe it's defined to have ints between the value of 0 and 10, okay? We've deliberately left the range checking out of this code because it's not important, okay? What is important is our small int class stores an int and has a constructor that takes an int, okay? And it can be used like this. We can say small int s is got the value 1 and small int t has got the value 2, okay, up on the left-hand side. Okay, and that works, that's fine. Now what we want to do is we want to be able to put small int into a vector, okay, so it gets copied in. We want to be able to use standard sort to sort that vector, and we want to use standard copy to see out and print out the details of that vector, okay? But we can't do this at this point. The reason why we can't do this is because we don't have the less than operator defined. So, here is the correct version of how we do it. We first of all do two things. We overload the less than operator, and we also overload the output stream operator so we can print out our small ints. Okay, so this is our .h file, okay, looks like that. And our .cpp file looks like this. The less than operator is overloaded to just be the value data member less than that value data member. And for small int, that's really easy, okay, because we've literally just wrapped an int. For less than, okay, less than does not mean less than. Less than means output redirection. Output redirection gets passed in the output file stream and redirects s.value into that output stream there, okay? And so sort requires this less than operator to be defined. It's really easy to write. The less than operator returns a bool. As operator less than takes in two const references, returns some sort of boolean which works out if one's less than the other one. This is a very simple example. There might be cases that you have to do more complex examples. As I stated before, this, not this exact question, but a very similar question to this is in the exam, and it's as simple as writing those 3 lines, okay? But people will stuff it up, so pay attention, yep.
Would you actually write less than or equal to? I would write less than?
Pardon?
If it's a less than, why are we writing it less than or equal to?
Is it less? Oh, that would be up to you.
Right.
Okay, that would be up to you. So if the question is, why are we defining less than as being less than or equal to, it would be up to you. It's not going to make a huge amount of difference, okay? Because one of them is going to be true, one of them is going to be false. If they're equal, it doesn't make a difference, okay? So sort requires the less than operator. For O-stream iterator, which we saw in week 2, requires the double less than, so for output redirection to be overloaded, okay? So let's go take a look at the assignment operator. Okay? So we just looked through the first hour today at the assignment operator in the sense of assignment copy. Okay? But what happens if we want to assign something of a different type? Okay? In this case, we have a member function that assigns stuff from the input stream, from the keyboard. Okay? So we can also define operator equals, and this is an overloaded function in addition to our copy assignment operator. Take in an input stream, and we can read some of that data in. Okay, this is a member function. Okay? And again, this returns a reference to the left-hand side. You don't need to do this in assignment 2. Okay? In assignment 2, you've got to do slightly different things with different data types, but you can assign from different data types. This exact thing here is how you can basically do some of your own casting. This here allows you, say if this was an int or a double, this type of operator overload allows you to take in a different type and assign it in to something. It allows you to do some sort of type conversion. Okay, so this is basically inbound type conversion. This is, we have some object and we're going to copy it across somehow. And we're going to define how we copy it across. Probably on Thursday, because we're not going to have time today, but on Thursday we're going to talk about how we enable our class to be casted to a different type of class. Okay, our grand tour of all the things that we can overload continues with the subscript operator. Okay, so the square braces, a bit like an array, but it's not exclusively for an array. You can already do this on a vector. On a Euclidean vector, you're asked to do this. This is defined as a member function. It often is defined in terms of an index. Okay? And so the argument passed in is the index. And if we're setting a value, the result is stored at that given position. We also return a reference to the L value at the reference. Note, for operator square brackets does not exist. Okay? So your two-dimensional array operator like that doesn't actually exist. Your two-dimensional array operator will be something along the lines of an array of arrays. Okay? And it works out how to handle it. Okay? So here's an example of how it might work. There's 2 versions of this. The reason why there's 2 versions of this is incredibly important. It's to do with when they get printed out. You need a const version and a non-const version of this. Okay? The const version returns an L value reference. The non-const version returns an int, which is a value, or as we learned previously, it's an R value reference. Okay? There's 2 overloads for the subscript operator. The top one is not const because it allows you to set. The bottom one is const because it allows you to get. Okay? I've got some code up on the right-hand side called safe array test. Safe array test does a couple of things. It creates a safe array, which is this class, creates an array of space for 10 elements. On line 7, or line 2 of main, we attempt to call the function for setting, this line 8 on this left-hand side. We attempt to call this one. Okay? And we attempt to write into location 12 for value 2. Now, clearly this isn't going to work. It would work if it's a real array. Our safe array does some bounds checking to ensure that this doesn't happen, okay? But imagine this does work. This code will call this not in const version. The cout down here that says S2 will call the const version of this. Okay? Yep.
It works fine with just the set function.
Now you say it works fine with just the standard function.
Yeah.
It won't work if I make a const object. Now it won't work. Now that one on line 7 definitely won't work. If I didn't have the const version at this point, this one wouldn't work either. Okay? This is about const correctness is really important. Okay, so we're going to keep returning back to const correctness. Okay? Const objects can only call const functions. Const functions are the ones with const on the end of them. Non-const objects can call functions that are both const and non-const. Okay? And you need to know when they get called. Okay? Again, assignment 2 asks for things to be const correct. And the reason for that is because sometimes you'll need const versions, sometimes you'll need a non-const version. That's why you often need 2 versions of these functions. This overload looks a bit like this. The square braces get overloaded and doesn't assert to make sure it's within bounds. Okay? Same with this one. The return type, return value looks exactly the same. But because this return type is different, remember one's returning a reference, an L value reference, the other one's returning a value. One that returns a value is const. One that returns the reference is not const. It doesn't make sense to have a const function that then also returns a reference to something. Okay? And so, like we've seen, we've got some user code. This code, by the way, goes and compiles. And when we run it, we get the runtime assertion thrown saying this thing didn't work. Okay, abort. By the way, you really shouldn't be using asserts in your code. You should be using tries and catches and exception handling, but we'll cover that next week. Okay? So if you try to run this code, the compile is fine. It's the run that will cause the exception. Okay, so this is a very quick and dirty way of being able to make an array that's safe. Okay? So let's talk about increment and decrement operators. Okay? You can define your own increment and decrement operators. And there's 2 versions of each. Plus, plus, minus, minus, x. X plus, plus, x minus, minus. One is L value, one is R value. They are different, and they operate differently. The prefix, so the plus plus x, returns a reference. The postfix returns a value, and it does more work. When people write for loops, so for int I equals 0, I less than some sort of size, who writes plus plus I and who writes I plus plus? So who does for prefix? Who writes plus plus I? Anyone? A couple of people. Who writes I plus plus? Most people. In C++, we prefer plus plus I. Okay? The reason for that is the L value version does less work. And I think the next slide is going to explain it. If not, I'll have to wave my hands about and explain it. Okay, I'm going to come back to explaining it, but the short version of what's going on is for plus plus, the prefix goes and modifies the code for L value directly. The x plus plus, which is an R value, remember R value is temporary, has to go get the value, increment it, create that as a temporary, and then copy it back across into the original thing. And so performance-wise, that's a lot slower. So now, as I did when I learned about this, I went and modified all my code, all my C++ code to go plus plus I instead of I plus plus. And I learned at Optimizer, this is an amazing thing, but Optimizer does it already for you. Okay? So you should know the difference between the 2 plus pluses, so for postfix and a prefix. Okay? but particularly with for loops, for optimizer should work it out for you, okay? But still we prefer to have plus plus I rather than I plus plus. And so we can overload these things as well. Here in this example, we have a clock, and this clock is going to tick. And this clock can also be changed by like clock plus plus or plus plus clock. The prefix returns a reference, okay, because it's returning an L value reference. The postfix returns a value, so the R value. The reason why these work as overloaded types is not because of the return types. It's because of the arguments coming in. So a postfix takes in an argument of an int. Okay? The way in which these might be implemented in terms of how they actually work is the prefix. So the plus plus simply calls this tick function that ticks the clock across. It returns a reference to itself. The postfix operator, plus plus, int, first of all creates a copy of the clock object. Okay, it's going to take some time to do the copy of it. It's then going to call tick on this thing that it's got. Okay. It's then going to return the C object. Okay. Actually, this should be C.tick, but anyway, it doesn't matter. It's going to return the original object back. This, yep, Sean.
It shouldn't be C.tick.
Shouldn't be C.tick. Okay, why?
It returns what it was beforehand. So
That's
you
right.
get different return values from the two.
Yeah, that's right. Sorry, I got that wrong. Okay, let me explain that again. Prefix. Prefix increments before we get the value. Okay? Prefix increments before we get the value. Postfix increments after the value has been used. Okay, I'm making sure I get this right this time. Okay? So, we create a copy. We increment, well, where else we currently are. We return the copy. We return the thing that hasn't been modified at this point. Okay? And so there's a whole lot more work that goes on at that point. Okay? So a prefix is preferred, particularly with for loops. The postfix is still there because there might be a reason why you want to get the value of something and then increment it. Okay? There can be reasons why you do that. Okay? So this slide is correct. It's very easy to get confused though. Okay, so let's look at pointing and arrows and dereferencing. Okay? We can overload for arrow and we can overload for star to provide pointer-like behavior of our classes. Okay? And so from next week, we're going to talk about smart pointers. Smart pointers are classes that behave like pointers when the arrow is overloaded. And we're going to look at a thing in the C++11 library called unique pointer, shared pointer, and weak pointer. In the textbook, they have a class called hasPointer. Okay? The overload for the arrow is a member function, and star is normally a member function. And it works like this. If the thing being pointed to is an ordinary pointer to an object, then the compiler will access that member pointer. If the pointer itself is an object that defines the pointer to a thing, then the compiler will access that operator overload call to a point, okay? Else there's an error. So basically, what that's saying is that pointer, that arrow pointer, should always go and return what something's pointing to, even if it has to go through a couple of chains to get there, okay? And so, so for arrow to work, it must return either a pointer to a class type or an object of a class type that defines its own pointer to overloaded operator. Okay? And so here is the first smart pointer that you're going to see. This smart pointer, called stringpointer.cpp, is a class that, in this case, yeah, this will work. Okay, we're going to rely on the default constructors at the moment. Okay, got some default constructors, but destructor deletes this pointer. Okay, so this class is a wrapper around a pointer to a string. The destructor deletes the pointer. Okay? This way you don't have to remember to delete your memory. It deletes it automatically. Okay? So I use a code. String pointer p equals new string smart pointer. When that goes out of scope, it's automatically deleted. Okay? So this is using unnamed objects to prevent memory leaks. Okay? And so part of the reason why we haven't talked too much about dynamic memory is A, it's still coming up, but second to that, we're going to be using smart pointers everywhere. Basically, from next week, you're never going to see a raw pointer again, I hope. Okay? And so the basic idea behind all smart pointers looks like this. We have a constructor that comes in and assigns the pointer to that value. So we copy that pointer. We don't copy from memory, we copy the pointer. A destructor deletes that pointer. So the destructor, when it goes out, automatically deletes. The overloaded arrow returns the pointer, and the overloaded dereference star returns the dereference of that thing it's pointing to. Okay? So inside our main function, we can create a new string, smart pointer, wrap that pointer inside the smart pointer object, and then we can dereference it like that. We can call p pointing to size. Okay, here's a quiz for you. This p pointing to size, we don't have size defined up here. How does it work? How does line 17 of that slide work? What happens? Someone want to tell me?
Does it go to the standard string?
Goes to the standard string and calls the size function on standard string. So what happened was this returned the pointer to standard string, which then the compiler automatically went and found the size function inside standard string. Okay, so there's no size method defined here. Overloading this arrow allowed us to automatically move on and go to that string and call the size function on that string. Okay? This is the basic idea behind all smart pointers. You won't need to define these classes yourself because there's one is provided in the libraries. Okay? But this is the basic idea behind how they work, and you should have this idea. Okay? So we basically have a class that wraps the pointer that looks after for deletion for us. So when something goes out of scope, it automatically gets deleted because we've got the deleter defined. Let's talk very briefly about casting. Okay? There's two ways to cast. There's single argument constructors, old types to new types. So we saw that last week, whereabouts we had our class being equal to something that wasn't the same type. And that was because the single argument constructor came in. Okay? And we talked about explicit constructors. What we now want to be able to do is create an operator that overloads a type call method. Okay? And this is const. Okay? Conversion operators must be defined as member functions. They do not take any parameters, and they do not specify a return type. And typically, conversions don't modify the object and are declared const. So, in assignment 2, you're asked to define a way of being able to cast your Euclidean vector back to a normal vector. Give you a giant hint, this might be the code to do it. Okay? Here is a class called teeny. This teeny int class is basically like a small or something like that. Okay? We want a way of being able to cast teeny objects back to int objects, or be able to use them, okay? So here's some code. We construct a teeny object t1 with value 1. We print out t1 plus 1. That's the equivalent of calling int, so cast t1 to an int plus 1. Because this operator int, brackets like that, const, does that conversion for us. Okay? Now, there might be more details that need to go inside here. It depends what you're doing. Okay? Depends what you're doing. We can also be explicit about these things. So we talked about explicit in terms of constructors. This is explicit in terms of operator overloading. We have tiny t1 like before. We get an error now if we start to say t1 plus 1. Because we can't implicitly, we can't just infer that we want that conversion to happen. But if we call static cast to an int, it calls that function explicitly, and it works. Okay? So this explicit is kind of important, kind of helpful. Okay? Because it allows us to be very verbose, very clear about what we're trying to do. So user-defined conversions are useful because a constructor can specify type conversions, okay? But it cannot specify a conversion from a user-defined type to a basic type. So we can't define a conversion in a constructor, say, to an int. But through this operator overloading, we can define how a class could be cast to an int, okay? And a constructor can't specify how a conversion from a new class to an existing class happens if you can't modify the existing class. So if I've got class A and class B, so I can only modify class B. I can't modify class A to create a constructor that takes in class B. But in class B, I can define an operator overload for how you could cast class B to class A. Okay? But be very careful about confusing operator overloading with the conversion operator. Say I've got for overload for operator plus on teeny and teeny, and I try to say this is teeny t and this is int I. And so I try to say t plus I. Is this confusing? Because we don't know if we should call for operator plus for teeny t, that conversion there, or for conversion that way round. Okay? So you should only overload what you need, and you should be very clear about it. Okay? And so we have some text here, which I'm going to stop at this point. We're going to pick this up next week. Oh, not next week, so we're going to pick this up on Thursday. But that's operator overloading. Okay?